Let's look at a few practices that are common to writing mechanisms for polar reactions. The first is that nucleophiles donate electrons to the electrophile, and we'll look at that more in depth in just a minute. We are still using electron pushing arrows or curved arrow notation to show the flow of electrons. You saw that with acids and bases. And then we also see a common intermediate called a carbocation. So let's look first at the nucleophiles and electrophiles. Nucleophiles are electron rich. They could be negatively charged. They have a lone pair of, and they also have a lone pair of electrons. But here are a couple of other examples besides the negatively charged ones. Here's one just with a lone pair, but neutral. And here we have a carbon that is electron rich because of inductive effects from an electron donating group that's donating electron density to the more electronegative carbon in this case. Pi bonds are also nucleophilic. On the other hand, with electrophiles are either going to be positively charged or electron deficient in some other way. They could have an electron withdrawing group on them that is pulling electron density away from the partially positive carbon in this case. And they could have that full positive charge and have an empty p orbital. In both of these cases, they can accept electrons. So when we write our mechanisms, we write mechanisms to show bond breaking and bond making between those nucleophiles and electrophiles. And so if we just look at the directions that the arrows are going in all of these examples, you'll see that they go from the more electron-rich site, like a lone pair bond. Let's bond over here, the bromide, to someplace that is electron poor. And so, for instance, this proton is electron poor because bromide is more electronegative than hydrogens are. Let's see, so this oxygen is electron poor because it has too many bonds and not enough lone pairs. This is electron poor because it's positively charged. It's a carbocation, and so is this over here. So in each of these cases, a nucleophile is forming a bond to an electrophile. So note that the start of we started drawing the arrow at the nucleophile, and it points toward the electrophile. So these are 4 different common types of arrows that you're going to see: proton transfer, loss of a leaving group, carbocation arrangement, and nucleophilic attack. And so you have seen some of these before. Certainly the proton transfer is one that you've seen before. It is possible to have multiple reaction arrows or electron pushing arrows in the same mechanistic step. For instance, in an SN2 reaction mechanism, we both have the formation of a new bond between the lone pair of an oxygen and this carbon here, and the loss of a leaving group occurring in the same step. So in other reactions, and really the only way that you know if you have one reaction mechanism or another is to go into the lab and do like kinetic experiments to figure out which type of mechanism you have. But comparing the mechanism we just looked at, which is a single step, so we have this formation of a new bond and loss of a leaving group in a single step to give overall a substitution reaction. Compare that to this other mechanism. It's also a substitution reaction, but in this one it takes 2 steps. And in the first step, the leaving group leaves, and in the second step, the nucleophile bonds to the carbocation intermediate. So this is a case where we have a carbocation intermediate forming. And again, this is an intermediate that you're going to see in many different reactions. So really the focus right now is to focus on this carbocation intermediate. We're just using the substitution reactions as examples of where you might see that. So let's look more closely at carbocations because we're going to see them so frequently. Carbocations are trigonal planar, so they're sp2 hybridized. They have a p orbital, and it's basically just a carbon with a positive charge. They are stabilized in a bunch of different ways. They're stabilized by being more substituted. So a methyl carbocation, a carbocation with just 3 hydrogens bonded to it, is the least stable that's being shown here. And then the most stable is a tertiary carbocation. That's where you have a positively charged carbon that's then bonded to 3 other carbons. So as we go up here, what we see is that those carbons are inductively donating some electron density, which stabilizes the carbocation. The other thing that those CH3 groups or carbon-hydrogen bonds next door to the carbocation do is stabilized by hyperconjugation. And hyperconjugation sounds like it's like the super crazy high energy stabilization or low energy stabilization, I should say. But something that's super strong. But that's not the case. It's actually pretty. It's fleeting, but it can add up. And so what happens here is that the carbon-hydrogen bonds next door to a p orbital can donate just a little tiny bit of their electron density as bond rotation occurs to the positively charged p orbital. And so the more CH groups that you have around your carbocation, the more stabilized the carbocation will be. So carbocations can also be stabilized by resonance. So here are a couple of examples for that. This is called an allylic carbocation, and so that's when you have a positive charge adjacent to a double bond, or you could have a benzylic carbocation where a benzene group is next door. And in all of those cases, you just get really nice p orbital overlap. You can see that. And the p electrons or pi electrons can be shared and delocalized so that that positive charge is spread out. So if you do have a high energy carbocation, one that's not very stable, the carbocation will rearrange if it's possible for it to become more stable. And so here are 2 types of rearrangements. One is called a hydride shift, and this is where a hydrogen, along with the 2 electrons in each bond, so that's H-, which is a hydride, it can jump over to the carbocation, leaving the carbon that it came from positively charged. And alkyl groups can also do this. So here's what you do if you're trying to figure out if a hydride shift or an alkyl shift occurs. And that's what you want to do is you want to look at your carbocation and then look at the positions next door. And so, for instance, there's a hydrogen here and there's 2 hydrogens here. If this hydride shifts over to the positive charge, the carbocation, as shown down here, what's left is a positive charge on a tertiary. It's a tertiary carbocation, and so that's more stable than the secondary carbocation. So this hydride shift would occur.